So today we'll look at the derivative rules for our trig functions. We are going to derive what the formulas will be. So first, it's important to talk about that in this course, whenever we talk our trig functions, we're talking in terms of radian measure. So all these derivative rules are in terms of radians throughout the year. When we're using these, we're always going to be in radians. It's okay if you want to think of your angles in degrees, but when we actually plug them in, we've got to plug it in terms of radians. So just some quick review first. We have 1 over sine x. That's just the same as cosecant x. If we have 1 over cos x, that's the same as secant x. 1 over tan x is the same as cotangent x. And your quotient properties, sine x over cos x is the same as tan x. And cos x over sine x is the same as cotangent x, the reciprocal of tan x. Just reviewing our sine and cosine graphs. So we've got pi over 2, pi, 3 pi over 2, and 2 pi. And we'll call, say, this -1 and this 1. So sine always starts at the wrap line, so it's starting at 0, then it's going up to the top, back to the middle, down to its minimum, and back to the wrap line. So your basic cycle of sine looks like that. Using this, we are going to try and graph what the derivative of sine would look like. So we'll start out, we'll just put our scale in place. And what we'll first do is we'll look and see where there are horizontal tangent lines. So at pi over 2, there's a horizontal tangent line, meaning our derivative should have a y value of 0. So at pi over 2, we'll plot a y value of 0 for the derivative of sine x. Likewise, at 3 pi over 2, we have a horizontal tangent line, so we'll put that there. And roughly, if we draw on some other tangent lines at 0 here, roughly that has a tangent of about +1. Here at pi, we have roughly -1. And when we get to 2 pi, it's about back at 1. So we just plotted our y values for the derivative based on what the slope values were in the original. And if we connect those, something should look familiar. Here's it drawn out all the way, going all the way to -2 pi on the left. Our derivative graph should look like cosine. Notice we're starting at 1, then going down, then we're at -1 at pi, and so forth. So our hypothesis is that the derivative of sine x is cos x. So we are going to try and show that now. We'll do it using our definition of the derivative. So we'll do the limit as h approaches 0 of sine of x plus h minus sine x all over h. And this is going to be a bit of a lengthy process. You're going to want to make sure you have plenty of space. Sine of x plus h, we will use our angle sum formula that you saw back in trig. Now, any of those types of formulas that you have to use ever and you're unsure of, they all are in the front cover of your textbook if you're ever working on a problem and need them. On your trig reference sheet, it was sine of a plus b, and it told us that that was equal to sine a cos b plus cos a sine b. Well, in our case, a is just the x, and b is just the h. So we'll have the limit as h approaches 0 of sine x times cos h plus cos h times sine, oops, sorry, cos x times sine h. And then we've got the minus sine x, and we're all over h. So what we're going to do is we're going to split this up into separate parts. We're going to rewrite this as the limit as h approaches 0 of sine x cos h, and then we'll take the minus sine x and put it all over h. And then we'll take the middle part and we'll do that separately, plus cos x sine h all over h. Well, on the left part, we can pull a sine x out of the top. So this will be the limit as h approaches 0 of sine x times cos h minus 1 over h plus, and we're going to write this as cos x times sine h over h. And the reason for doing this is we kind of want to isolate the stuff that has h's in it. Because what we'll do is now use our limit laws that we can write each of these as their own limit. So the limit as h approaches 0 of sine x times the limit as h approaches 0 of cos h minus 1 over h plus the limit as h approaches 0 of cos x times the limit as h approaches 0 of sine h over h. And our rules from Unit 2 are what allow us to do that. Well, the limit as h approaches 0 of sine x. There's no h's to even sub in for, so you can go ahead and imagine you're doing direct substitution, but you're not really subbing anything in, and you just get back sine x. Okay, because h isn't involved in that at all. This we're going to hold on to for a second. It's going to be a little tricky, and we'll come back to it. Plus, limit as h approaches 0 of cos x. Well, there's no h's, so imagine subbing in 0 for h, but there's nowhere to put it, so you just get back cos x. And then the last thing we saw in Unit 2, we did it with a table. We evaluated this limit, and we saw that it kind of looked something like that. So it got closer and closer to the value of 1. Now when we saw it, we just saw it with x's. We had the limit as x approaches 0 of sine x over x. But we saw that that was just equal to 1 back in Unit 2. So we can replace this with 1. And now we have the task. We've got to figure out what the limit of h approaches 0 of cos h minus 1 over h. So we'll kind of do an aside to figure that out. So we'll have the limit as h approaches 0 of cos h minus 1 over h. And what we'll do is we'll multiply top and bottom by the conjugate. So we'll have cos h plus 1 over cos h plus 1. When we FOIL out the numerator, we'll get cos squared h minus 1 over h times cos h plus 1. Now, I'm going to use h's instead of x's. We know sine squared h plus cos squared h equals 1. If you subtract the sine over to the right and the 1 over to the left, you'll get cos squared h minus 1 equals negative sine squared h. So we can replace our numerator with a negative sine squared h. And we're going to split this up to make it easier to evaluate. We'll write it as sine h over h times the limit as h approaches 0 of negative sine h over cos h plus 1. And our reason for doing this is that left-hand limit there, we know the limit as h approaches 0 of sine h over h is just equal to 1. Again, that was the example we saw back in Unit 2 that we did with a table. And on the right here, this is something we can do direct substitution with. This will end up equaling negative sine of 0 over cos 0 plus 1. Well, sine 0 is 0, so we'll get 0 on the top. Cos 0 is 1, so we'll get 1 plus 1 is 2. So we'll get 0 over 2, which is just 0. So really, this whole second part is just 0. And 1 times 0 is 0. So what we've just shown is the limit as h approaches 0 of cos h minus 1 over h is equal to 0. And that was that question mark we had in our formula. So we'll go back. We now know that this question mark is just 0. Well, a sine x times 0 is 0, plus cos x times 1 is cos x. 0 plus cos x is cos x. And we just showed that our derivative of sine x is equal to cos x. Now, I would never expect you to have to do something like this on a quiz or a test. This was merely to show you the mathematical way of how you can show that the derivative of sine x is cos x. We were able to kind of eyeball it with the graph and piece together the derivative graph to figure that out, but this is the algebraic way you would go about showing that the derivative of sine x is cos x. I would expect you to just memorize that. I would not expect you to show this on a quiz or a test. So there we have it. Our derivative of sine x is really just cos x. Well, now let's see what's the derivative of cos x. And we'll go through the same process. We'll do our definition of the derivative. So we'll do the limit as h approaches 0 of cos x plus h minus cos x all over h. We're going to have to use another angle sum formula. Again, if you don't remember those, they are in your front cover of your textbook if you ever have to refer to them. In trig, you saw it written as cos of a plus b. And you saw that was equal to cos a, cos b, minus sine a, sine b. So we'll have the limit as h approaches 0 of cos x, cos h, minus sine x, sine h, minus cos x, all over h. Like the sine derivative, we'll do some splitting up to make it look a little nicer. We'll have cos x cos h minus cos x all over h minus sine x sine h all over h. And we'll pull out a cos x. So we'll have cos x times, we'll still have cos h minus 1 all over h, minus, and we'll rewrite this as sine x times sine h over h. And we'll just do each of our limits individually. We'll have the limit as h approaches 0 of cos x times the limit as h approaches 0 of cos h minus 1 all over h, minus the limit as h approaches 0 of sine x times the limit as h approaches 0 of sine h over h. Well, the limit as h approaches 0 of cos x, there's no h's in there, so we know that's just cos x. Limit as h approaches 0 of cos h minus 1 over h. That we did out a second ago, and we saw it was 0. minus limit as h approaches 0 of sine x. Well, there's no h's in there, so it's just sine x. And the limit as h approaches 0 of sine h over h, we saw that's 1. Cos x times 0 is 0. Minus sine x times 1 is sine x. So we end up with a negative sine x is our derivative of cos x. So if I told you that f of x was equal to sine x, then we know that f prime of x, the derivative we've said, is cos x. If we want the second derivative of that, that would be taking the derivative of cos x, which we just said is negative sine x. Well, if we want the third derivative now, we can use the fact that we know we can ignore the minus 1 out front and just take the derivative of sine x and multiply the negative 1 back in. Well, the derivative of sine x we know is cos x, and then bring your negative 1 back in, so you get the derivative of negative sine x is just negative cos x. And then if we do the fourth derivative, again, forget about your negative, the derivative of cos x is negative sine x. Bring that negative back in, we have minus a minus, now making it a plus sine x. So if you notice, it just cycles through. Derivative of sine x is cos x. Derivative of cos x is negative sine x. Derivative of negative sine x is negative cos x. And then that derivative, you're back to sine x. So it just cycles through every 4. This is a cycle I would strongly suggest memorizing. We will see it hundreds of times throughout this school year. Okay, let's look at some trig derivatives in a product rule. Well, we can do derivative of the first part, so 2x times regular of the second, sine x, plus regular of the first, x squared, times derivative of the second part, cos x. Okay, and then I would say just leave it like that. Now again, you could have reversed your order with product rule. You could do the regular of x squared times derivative of sine x, and then flip-flop it for the second one. Because it's a plus, you can do it either order. Now let's see if we can find the derivative of tan x. Well, this should be a little bit easier than the sine x and cos x ones, because we know tan x is really just sine x over cos x. So rather than doing it with a definition of a derivative with limits, we can just use the quotient rule. So we'll do low d high minus high d low all over low low. So low will be cos x. D high, derivative of sine x would be cos x. Minus high, sine x. D low, derivative of cos x is a negative sine x. All over low low. So we'll have cos squared x. Now remember, we write it as cos squared x, but what that really means is cos x, the whole thing in parentheses, squared. So if you ever need to put it in your calculator, that's how you'd have to put it in, but the notation we use is the squared coming right after the s. Now this we're going to neaten up. Cos times cos will give us cos squared x. Minus sine x times another minus sine x will give us a plus sine squared x. Because a minus times a minus is a plus. All over cos squared x. Well, we know that sine squared x plus cos squared x is just equal to 1. So we get 1 over cos squared x. 1 over a cos is just a secant, so this is really just secant squared x. So our rule then is the derivative of tan x is just secant squared x. Next, we'll look at cotangent. We can rewrite cotangent as cos x over sine x and do a similar thing to what we just did. We'll do low d high minus high d low all over low low. So we'll have sine x, our low, times derivative of the high, derivative of the top. Derivative of cos is negative sine x. Low d high, now we have minus high d low. So cos x Derivative of sine x is cos x. All over low, low, so sine squared x. Sine x times the negative sine x will give you negative sine squared x. We have a minus cos x times a cos x will give you a negative cos squared x. All over sine squared x. Well, we can pull a negative 1 out of the top, and we'll have sine squared x plus cos squared x left in parentheses, all over sine squared x. We know that sine squared x plus cos squared x is just equal to 1, so we'll have negative 1 times 1 over sine squared x, which is just negative 1 over sine squared x. Well, a 1 over a sine squared x is just a cosecant squared x, so we'll have negative cosecant squared x. So if you want to write down your rule, and we'll have these all on one page in a second, but derivative of cotangent is negative cosecant squared x. And we'll go through our last two that we haven't done yet. Our derivative of cosecant x, we're going to rewrite that as 1 over sine x, and again use the quotient rule. Low is sine x. D high, derivative of 1 is 0, minus high, 1, d low, cos x, all over low, low. So that's sine squared x. Well, this will go to 0, so we'll have negative cos x over sine squared x. Think of this as a negative cos x times 1 over sine squared x. And we're actually, let's split up the sine squared x. We'll put one of the sines here, and we'll write this as 1 over sine x. So we just split up where the sine squared x was. One of these is a cotangent. One of these is a cosecant. So this will just become minus. The way we have it written, we've got the cotangent x first and the cosecant x second. So this would be our derivative of cosecant. And you could do minus cosecant x times cotangent x because multiplication is commutative. And we've got one last one to look at. We've got 1 over cos x. So we'll do low, cos x, d high, 0, minus high, 1, d low, derivative of cos x is a negative sine x, all over low, low, so cos squared x. This will give us negative 1 times negative sine x will be a positive sine x over cos squared x. We'll do like we did last time. We'll write one of them as a 1 over, so we'll do 1 over cos x times sine x over cos x, and you could do that in either order, it doesn't matter. 1 over cos x is just secant x. Sine over cos is just tan x. So our derivative of secant x is just secant x times tan x. So here's a list of them all together, so you could copy them down in one spot. You're welcome to pause it and take the time to copy them down if you'd like. You will have to commit these to memory. The sine and cos ones we will use, again, hundreds of times. The tan one we'll probably use at least 25 times throughout the year. And then the other three, maybe a dozen times throughout the year, we'll see those. So let's see if we can do a quotient rule with these now. We've got secant x over 1 plus tan x. We'll do low, which is 1 plus tan x, d high, Well, we've got the derivative of secant x, which we just saw was secant x tan x, minus high d low. So we'll have secant x, d low, derivative of 1 is 0, and derivative of tan x is secant squared x, all over low, low. So this is 1 plus tan x squared. Now, if all they wanted was the derivative, we would just leave it like this. But they actually have a follow-up question in this one. We want to know for what values of x does the graph have a horizontal tangent line? Well, it has a horizontal tangent line when the slope of the tangent line is 0. That means the y value of our derivative needs to be 0. So we need to know when this derivative is going to equal 0, which right now it would be a mess to try and do that. So we're going to have to try and neaten it up. So one thing is this is really just tan squared x plus 1. That comes from our Pythagorean properties. If we have sine squared x plus cos squared x equals 1, if we divide everything by cos squared x, that'll give you the tan squared x plus 1 equals secant squared x. So our secant squared x can be replaced with tan squared x plus 1. So we'll rewrite this as 1 plus tan x times secant x tan x minus secant x times tan squared x plus 1 all over our 1 plus tan x squared. Now, in the numerator, we have two separate terms. We have the two sets of parentheses multiplied first. That's a term. When things are being multiplied together, they're considered a term. And then we have the second set of two parentheses. That's a term. Well, each of those terms has a secant x that we can pull out. So we'll pull out our secant x. In this first term, we'll be left, basically this is gone, so we'll be left with a tan x times a 1 plus tan x. So we'll distribute that tan x through to give us tan x plus tan squared x. Again, where that's coming from is we just distributed that tan x to each thing. In the second part, this secant x is gone, but we still have the negative 1 to distribute to each thing. So we'll get minus tan squared x minus 1 all over our 1 plus tan x squared. Again, the reason for doing this is we need to find when the derivative is going to be 0, because that's where we will have a horizontal tangent line. Well, we've got a positive tan squared x and a negative tan squared x. Those add to 0. So now we just have secant x times tan x minus 1 all over 1 plus tan x squared. So a fraction is 0 when the numerator is 0. So we really just want to know when is secant x times tan x minus 1 equal to 0. Well, to do that, we'll just, it's already factored, just set each of the parts equal to 0. Secant x is the reciprocal of cos. So this is like saying 1 over cos x needs to be equal to 0. Well, if you have a 1 in your numerator, remember a numerator would have to be 0 for a fraction to be 0. If you have a 1 in your numerator, then you can never be 0. So we'll get no values of x that could possibly make this 0. On the other side, we'll get tan x is equal to 1. Tan is positive using your ASTC in the first quadrant and the third quadrant. And from your 45, 45, 90 triangle, tan of 45 would be 1. So we're really working with a 45-degree reference angle. So that's 45 degrees and 225 degrees. That's from 180 plus 225. But we can't do this in degrees. We need it in radians because all of our trig functions are in radians. So 45 times pi over 180, that'll end up giving us pi over 4. And 225 times pi over 180. Again, you did multiply. When you multiply, you want whatever you're going to be in the numerator. We're going 2 radians, so we want the pi in the numerator. This will end up giving us 5 pi over 4. Well, they want to know all of the values where it'll have a horizontal tangent line. These are where it will make it 0, but also if you just keep going around 360, it'll make it 0 as well. So we could have pi over 4 and just keep adding 2 pi on. And we say 2 pi n because we could do any multiple of 2 pi. And we'll have 5 pi over 4 plus 2 pi n. And we'll say where n is an integer. So n could be 1, n could be 2, 3, 4, 0, could be negative integer. So this is our general solution of all values of x that will give us a horizontal tangent line. That's all for today's video. We'll see you next class period.